I ran out of room on that piece of paper, so I'm starting a new page and I'm going to just remind us of what's going on here. We're fencing in a rectangular field like this. The area of the field, which of course would be x times y, is required to be 15,000 square feet, and we use that to get an expression for y in terms of x. Y is 15,000 over x. And then we use that to write a function for how much fencing there's going to be, and that was 3x plus 30,000 x to the negative 1 power. We decided that the domain of that function was 0 to infinity, so x can be any positive number. And because that domain is not a closed interval, we need to make a sign chart. For the sign chart, we'll need the derivative. That's going to be 3 minus, so I'm bringing that negative 1 power down front, minus 30,000 x to the negative 2, because I have to subtract 1 from the power. And now we want to simplify that so that we can find critical numbers. So let me write this as a fraction, 3 minus 30,000 over x squared. The common denominator would be x squared, so I'm going to multiply this 3 by x squared over x squared, at which point we have f prime of x equals 3x squared minus 30,000 over x squared. And I can factor a 3 out on top, so that gives me x squared minus 10,000 over x squared. And notice that 10,000 is the same thing as 100 squared. So I can factor that, and I get on top 3 times x minus 100 times x plus 100 over x squared. So from that we can see that the critical numbers are x equals, if x is a 100, we'd have a 0 on top, so our derivative would be 0. If x was negative 100, we'd also have a 0 on top, so our derivative would be 0. And then the other type of critical number is when the derivative is undefined, and that's going to happen when the denominator x squared is 0, which will happen when x is 0. So now I make a sign chart. I put my critical numbers in, and we're going to determine the sign of f prime of x in each interval. Except that this stuff is not in our domain. We said x cannot be negative. So we're just going to ignore that because we don't care what the function does over there because we can't use the function with a negative x. So now you can plug in numbers into your derivative. So for example, for this first interval, I could plug in, say x equals 1. And if you do that, you'll get a negative number. And then for the second interval, over here, that's 100 up through everything. If I plug in, say, x equals 200, I will get a positive derivative. Now that tells us that the function goes downhill in that interval and then uphill forever and ever after that. By the way, I know the textbook does not put in these uphill and downhill arrows, but please do put them in. I will look for those on your exam when I'm looking at your sign chart. And there's a couple of reasons I want to see those there. The most important reason is that that gives us a nice visual of what's happening. We can see that the function must be doing something like that. And I think that you'll find that helpful. The second reason is that way I have a confirmation that you understand what these signs of that derivative are telling us. So please put in these arrows. Okay, well we can see from that shape that the function must have a minimum, an absolute minimum, at x equals 100. It's a local minimum, but it's also an absolute minimum. It's the lowest spot on this domain. So there could be lower spots for the function over in the negative numbers, but we don't care about that because we can't actually have a negative number in this actual situation. So our absolute minimum occurs at x equals 100. So let's see if we can tell the farmer how he should make his fencing. The y has to be 15,000 over x, so that's 15,000 over 100, which is 150 feet. So the field should look like this and that, and these are in feet. And the amount of fencing needed, what will that be? Well, f of x we said was 3x plus, actually let's go back to the original fencing function. So that was 2x's plus 3y's. And we're saying that our x should be 100 and our y should be 150. So what's that? 200 plus 450? So 650 feet of fencing will be needed. That's the minimum amount of fencing you can use to enclose 15,000 square feet in this fashion.